Well, good morning, everybody. I'm Jeff Hall, the director of Lowell Observatory, and welcome once again to our weekly Cosmic Coffee live stream, where we touch on a different topic related to astronomy and science and some of the things we do here at Lowell. I'm joined today by our educator, Victoria Girgis, who's on the screen with us here today. Victoria is one of the educators in our outreach programs. She's involved with our interactive stargazing program, which we'll be talking about today. And she happens to be the one who acquired the now world famous image of the first launch of Starlink satellites a little over a year ago. And we'll touch a bit on that this morning as well. As always, first, we're going to give a quick shout out to one of Flagstaff's many little coffee shops. And today we'd like to shout out to Fat Man Coffee across from the Flagstaff Mall, a nice little drive up there where you can get a really good cup of brew to get you going in the morning. As always, as we recover and deal with the pandemic, be sure to support our local businesses that are struggling to make it through this. So we'll start off today talking a little bit. Victoria, why don't you tell us in general about the telescope viewing that we offer here at Lowell, both before we had to close down and what we're doing now with this interactive stargazing, and how we sort of changed the programs to accommodate the new world order here.
Sure. So our previous programs, at least a few years ago when I first started, were largely telescopes that we would wheel out in front of our rotunda plaza, and we had to manually point them at various objects in the night sky, ranging from galaxies to globular star clusters, to stars themselves, to planets. And nowadays, with our Giovanni Open Deck Observatory, that has changed in and of itself, because all of our telescopes are now controlled using iPads. And so we no longer have to manually point the telescopes, but it's still largely the same guest experience. What we've tried to give people is the experience of looking through a telescope with your own eyeballs. And there is something, I hesitate to say almost magical, but there's something about looking through a telescope with your eyes and having those photons travel through space, through a telescope, and then hitting you and seeing them yourself. And that's really the experience that we try to bring people.
It certainly is. I don't think magical is necessarily a bad word for it, given the reactions when people look at something like the Orion Nebula or Saturn. I think they can't believe what they're seeing a lot of the time.
Definitely. I've gotten the comment, that has to be a sticker about Saturn many, many times. And it's not. It's real.
So then talk about interactive stargazing, and then we'll talk about how we're delivering that.
So the wonderful thing about our programs is they are interactive, and even our formerly in-person and soon to be in-person again programs. The wonderful thing is we get to talk to people, and people bring up things like, oh, I've never seen Saturn through a telescope, and then oftentimes if it permits, we can point the telescope there. And so there's a level of interaction with other people that brings about kind of the spontaneity of it. And the interactions with other people fuel us. And so we're able to build on what they already know, what they know about the night sky, and instead cater the experience to them. And we've been doing that as well virtually using our Giovanni Open Deck Observatory telescopes in order to bring that same experience to people, at least through a computer screen, where they can still interact with us and interact with the night sky, albeit virtually.
Right, and I've seen a couple of these, and you all do a really fine job with them, and people obviously love it. You can tell that from the comments. So, all right, so I guess we can look at, I know you've got some interesting slides here. So, yeah, so what do we got here? Yes, I know what this is.
This here is a galaxy cluster called NGC 5353. One comment that we get quite a bit from a lot of people is how lackluster some of the names are. So this is pretty much a catalog number for a group of galaxies. And it's spectacular when you look at it. There's a collection of different galaxies in this image. In particular, you can see this one here has a nice spiral structure. You can see the wispy little arms, and it looks small to us, but really this galaxy is full of billions of stars, which is even more incredible when you think about it more. And there's several other galaxies in here as well. There's one here, another here, and I believe this one over here looks like one as well.
Mm-hmm. Yeah, and there's a rather different image of this, as I recall.
There is. This image was taken with our new 17-inch plane wave telescope up at the Godo, but this one was taken with our previous iteration of our photographic telescopes that we use, that we referred to as MALI, or the Malin cam, named for the camera that was in the telescope. But this image is different for other reasons as well.
Yeah, so this is obviously the iconic image. So this was, as I recall, it was about 3 days after the launch of the first set of 60 of SpaceX's Starlink satellites. And I mean, how did you get this? I got up the next day and you had posted this, and it was like, whoa! How did this all come about?
It was a warm summer night, and we were looking at this galaxy cluster, not because of anything Starlink related. There was, in fact, a supernova in one of the galaxies. And I'm not sure which one now, but there was a supernova in one of the galaxies, and you could see it. Supernovas are so bright that they can show up in a view of a whole galaxy. And so we were looking at this cluster of galaxies, and there were a variety of topics that we could engage guests on. Things like, what is a supernova? How do stars die? What are galaxies? So it was a really neat image to talk to people about a lot of in-depth things that they could then see on the screen. So that was why we had the telescope pointed at this particular spot in the sky. And it just so happened that the Starlink satellites were orbiting in this big long train, and they passed right in front of the telescope and right in front of the image.
So it was pretty much happenstance that you got this image.
Yep, it was pretty much just chance and luck.
Yeah. Well, it certainly became famous because this image actually got used in both the American Astronomical Society and the International Astronomical Union press releases that we issued after the launch of the Starlink satellites. I was actually one of the authors of those press releases because I'm presently the chair of the AAS Committee on Light Pollution, Radio Interference, and Space Debris. And this has obviously been in the news ongoing as SpaceX has launched one set of these 60 satellites after another. And obviously there's the potential for substantial impact to astronomy as well as to casual stargazing. The good news is that SpaceX has been very proactive, and they have put a lot of time and effort and money into trying to mitigate the effect of this and darken their satellites. And Elon Musk himself is on record saying that they will do what it takes to solve the problem for astronomy. In fact, this Cosmic Coffee episode is pretty timely because just next week we are convening a workshop. We've got about 260 attendees at this point. It'll all be virtual, of course. But it's a series of webinars on various aspects of the satellite constellation problem. And not only speakers from astronomy, but 2 speakers from SpaceX, including one of the engineers that I had a chance to speak with personally last January in Honolulu at the AAS meeting. And they really are going to great lengths to try and find ways to darken the satellites. Not launching is off the table. This is a new world up there. These launches are going to happen, and we are trying to get out in front of the problem, not only from the point of view of SpaceX, but other potential operators. And it's been a good and collaborative process. And the workshop next week has been commissioned by the National Science Foundation, and our charge is to deliver a white paper about exactly the image that you got a year ago. In fairness, I think we need to point out for viewers that this is an unusually disrupted image, because the satellites at this point had only been launched 3 days before. So they were still very low, very bright. They're tightly packed because they hadn't been spread into their operating altitude yet. So most of the time, at least to the visual eyes, the satellites are going to be considerably fainter than this, although I have seen some.
Yeah, and when we took this image, we did see them naked eye first, but they were also considerably brighter because this was a few days after their launch. But we did see them naked eye, and we could tell where they were headed.
This is in this low parking orbit. What SpaceX is doing is they launch them up, and they leave them in a lower orbit for a little while, like a week or two, which allows the orbit to process, and it gets them into the plane that they need to provide the coverage. And then they boost them up to their operating altitude, which is about 550 kilometers. And at that altitude, the raw, undarkened SpaceX satellites they're 5 to 5.5 magnitudes, so right at the hairy edge of what you can see with the unaided eye. Once they darken them, they won't be visible to the unaided eye, but these low ones certainly are.
Yes.
Well, it's certainly turned into an iconic image, and I see, Victoria Girgis / Lowell Observatory, and virtually every time there's a press release about Starlink. So certainly a famous image you captioned there with the humble old Celestron. So you've got a picture, I think, of these facilities to show people the difference in what we've been able to do now with the GODO.
So I think here, just the images of the two telescopes are a good way of showing the differences between them. So over here, on the left, we have our old Mallenkamp system, and you can see that it's a telescope on wheels. We had to wheel it out all the way across campus every night we wanted to use it. And I remember at least setting it up was always interesting, because we would try to set it up in the daylight when we could actually see what we were doing, but the telescope itself has to be pointed in order to align directly towards the North Star, which you can't see during the daytime or during daylight. So it was always interesting. It always required a lot of wiggling back and forth, and then the alignment was always just a tiny bit off. So anytime we'd send it to an object, it would not perfectly be centered, but still it got us there, and it was a wonderful telescope for the time we were using it. On the end of the telescope here, we have our camera, and that was about a 1 megapixel camera made by Mallenkamp. And then on the screen here, we can see an image of the moon that was captured with it. And then we can compare that with our other telescope over here, our new, I believe this is one of our plane waves. We now have a 17-inch and a 14-inch. Most of the pictures that I will show you today were taken with the 17-inch plane wave, though the 14-inch will be the new home of our photographic system, and will instead have a spectrograph on the end of the 17-inch. Once we finish sorting out all the bugs. But this one is permanently mounted. So all of our telescopes up at the GODO are bolted in place. They don't really move from their spots. And instead we can send them to different objects from that one spot. And as such, they're aligned much better and generally find things much easier. And another note on the size comparison is our former telescope was an 11-inch telescope. So now we have a slightly larger light collecting area. So that is not so much of a big improvement with our telescope, because you can account for how much light you're taking in by taking a longer exposure or adjusting the camera settings itself. But it is nice to have a slightly larger telescope because you can take in more light and see slightly fainter objects as well.
Yeah, and we've remarked, I think we were remarking last week, talking with Sarah and Miriam about just the efficiency of the Godo and having the telescopes permanently mounted. And I was seeing it myself last fall, just how much faster the lines moved because you all didn't have to constantly repoint the telescopes every 2 or 3 viewers.
Yep. Every 2 or 3 viewers, we would have to hop in there ourselves and take a look and realign the telescope.
Right. So we get to get a lot more eyes to the eyepieces, and it gives all of you the opportunity to do more of what you're supposed to be doing, which is, educating people about the universe, not moving telescopes around. We'll stop really quickly as we did have we got 2 questions come in. So one looks like it's probably for me, one for Victoria. First question from Anthony Kiefer. Good morning, Anthony. How are you? How much better are the newer, blacker Starlinks? So SpaceX has made 2 tries. One was, it was launched earlier this year. They called it DarkSat, and they literally just darkened one side of it. I don't know exactly what they did. And it darkened it by about a magnitude from 5th to 6th. The details of that will be reported next week, I know, at our workshop. More recently, they have, in the recent launches, deployed what they're calling VisorSat, which actually has a deployable visor that goes out after the satellite is launched, that I think is going to take them down closer to 7.5. And for the VisorSats, they have been working closely with some folks at the Vera Rubin Observatory, formerly LSST, Large Synoptic Survey Telescope, in particular with their project scientist, Tony Tyson at UC Davis. And Tony's been working with SpaceX on this under a non-disclosure agreement, meaning that they've been sharing technical and proprietary details of the satellites to try to maximize the amount of darkening. From our point of view, we've been working with SpaceX outside a non-disclosure agreement, so I don't know any of that proprietary information, which is good because I can just report to the press on what's going on without accidentally spilling the beans and creating a lot of problems. So that's the answer to that question. And I think the folks at the Vera Rubin Observatory are feeling like they're getting to the point where, the satellites are certainly not invisible, but mitigated to the point that they can be dealt with in the images. And that will be discussed at great length in just a whole variety of ways next week. And then question probably for Victoria from Terry Pantano. What was the size of the Celestron and what mount is it on?
Excellent question. So the Celestron telescope was an 11-inch telescope, and we had it mounted on a Celestron CGEM mount on wheels that we would move around. And so here's a couple of other details about the 2 telescopes and their differences. Most notably, the difference that I see is the difference in camera resolution. Our former system had a resolution of about 1 megapixel, whereas now we're dealing with the resolution of about 10 megapixels, almost 11. So even though the size of the sky that we're seeing is the same, because the field of view is the same, about the same, we can see more detail with our new telescopes.
Yep, resolution is a good thing. And for reference, that field of view means we can pretty much just about get the whole moon, right, in one image.
Yep, just about the whole moon.
Yep, it's about a half a degree. Okay, so maybe we can, for the rest of our session this morning, look at some of the cool things and sort of the differences between the old and the new.
Yeah, of course. So our first image here that I took the rest of these images throughout the time here, but these are 2 images of the Crab Nebula. And over here on the left, we've got the older system, and then on the right, we've got the newer system with a guest appearance from one single satellite. Mm-hmm. And I included this image not just because it's the best image of the Crab Nebula that I have, but because I thought it would be useful to show that satellites do exist in astronomy, and they are something that we have to contend with, but they're often more like this, where you get one satellite through the image, and not necessarily 60, which is why I think Starlink was more of an issue.
Absolutely. And I can't tell just from looking at the image, but it looks like that satellite streak is probably what we call saturated, meaning the pixels in the image are completely blasted with light to their maximum data value. And when that happens, this is the reason the satellite issue is a worry, is, these things can't be filtered out. And if they're bright enough, they can introduce other side effects into the image. So it's definitely a serious issue. And just, one or two streaks like this can force a researcher to have to retake the entire image. And sometimes for very faint objects, those are long exposure times. These are not like you have to redo it like that. You have to sit there for a while if you're observing really faint objects.
Yeah, which is one big difference between what we do in our public education programming and astronomical research is most of our exposures are under a minute. This picture of the Crab Nebula with the satellite might have been around a minute and a half maybe, but generally not more than that, because we don't want everybody to have to sit around a telescope for 10 minutes waiting for a picture to load. Instead, we want people to be able to see something at least, something that we can engage them and talk to them about, and interest them in the image, rather than just waiting around for it.
Right. It does come up quickly. It's kind of fun during the meet an astronomer nights when you've gone to a new object and you sort of build up the image, but it comes up pretty quickly.
And that's largely because we use these cameras that are geared more towards faster imaging.
And we do have a question coming in again from Terry Pantano asking, do we know what satellite that was? The answer, no. If I knew the exact time, date of that image, and I mean a very precise time, yeah, we could tell what it was, but I don't know which one it was. I can point out that I use a satellite tracker program called GoSatWatch. It's $10, but it's been well worth the effort. And I just pulled it up right now. I've got it customized. So it's showing right now all the Starlinks right there. And you can see how they go from plus to minus 53 degrees. And right here, you can see a little line of them. And that's one of the new launches. And so, we use these to try to identify when satellites are coming by. And it's just highly recommended if you're into this kind of thing and want to follow when there are passes of satellites, but also some of the really bright things like the International Space Station. There were some killer passes of it here in Flagstaff just a couple of weeks ago. So highly recommended if you want something to help you track that. Anthony Kiefer asks, how long of an exposure can you take with the telescope? How long can it track?
The telescope, I believe, could track as long as the object is in the sky or within several degrees of the horizon. I'm not sure exactly what the limits are, but we generally don't push it to those limits because of our visitor interactions.
Right.
And we like to either move between objects or keep it on the same object and have a updating picture of it.
Yeah, in principle, you could take a really, really long exposure, but there are a number of reasons, both from a tracking perspective, obviously visitor experience, and also some just inherent properties of the detector that we wouldn't just expose for that long. Okay.
Yeah. Eventually, if you exposed it enough, you wouldn't see much. You would overexpose. So there's a balance. All
right, what do we have next?
The Crab Nebula again. I thought I'd put the pictures in a little bit bigger. So with this one, you can see there's not a whole lot of detail in the nebula itself that you can see. And the other problem that we were plagued with our former system were these bright pixels. that we call hot pixels, and they're an error in the way the camera takes data. So they make it look like there's all kinds of bright little pieces of glitter.
Yeah. I mean, all CCDs have hot pixels. It's just a fact of life. But this one really had a lot of them. There were a lot of new stars in our images.
There were definitely. Whereas here, not so much. There are a handful of hot pixels, but you can't really see them, and that's partly due to the resolution as well. The resolution on this one is so much higher, so each pixel looks like it's a lot smaller as well. So that reduces the effect that those hot pixels would have. But with this image, you can see more structure with the Crab Nebula as well. And these are things that we would engage with guests about. Here you can see some filaments in this big gas cloud that's a dead star. You can see these lines and the structure of the nebula itself. And so this is where a lot of the interaction comes in with guests, because they maybe didn't know that stars can die like this and can explode and leave behind big clouds of gas and dust. And so they might ask, well, are there any other dead stars in the night sky that we can see right now? And I believe slightly different time of year, but there's also the Veil Nebula. So both the Veil Nebula and the Crab Nebula are supernova remnants. These are big stars that exploded and left their guts in this big cloud of gas and dust. And again, we have an image taken with our older Mallancam telescope on the left, and then on the right we have the newer plane wave telescope. And so with these different images, it's harder to see here, but we can get some of this structure and the different colors, like this pink that represents hydrogen in the nebula. But again, not maybe the best quality image. And so really the strength comes with our newer telescopes, where we do get these crisper, sharper images that show what we're looking at in much more detail. And guests can they get blown away by these images, and it's really something to see, because in our interactive stargazing, it's not like we're back in the warm room operating the telescope. We're out there with the guests operating the telescope, and so they can see what happens. Some of my best guest interactions have been with little kids who are really interested in how the telescope works, and I let them help me decide where to point the telescope. So it's a neat experience to be able to share this stargazing with other people.
That's certainly a dramatic improvement, particularly with this objects. The resolution clearly comes through here.
It does.
So a couple of questions. Jim Davies asked, can an occultation by an artificial satellite be used for science? Interesting question. The problem is these satellites are tremendously bright and very transient, and really are just stamping nuisance streaks into the images, unlike, say, a very distant faint object you might use as an occulting object for a star. Terry Pantano asks, is the new Mallancam a CMOS camera? It's a CCD, correct?
I believe it is a CCD.
Yeah, it is. Yeah. That's where the hot pixels in the old CCD were coming from. The new ones are much better.
Mm-hmm. There are still a few of them. I'm not sure if I can pick any out here, but there are a few.
Well, there's a lot of stars.
There are quite a few stars.
It's really neat for the meet and astronomers how nicely this brings out the colors. You can clearly see the different hues in here. And of course, the colors are a clue about the chemistry that's going on in the objects you're talking about. And maybe this is one thing we could mention to our viewers. We're showing here the images this morning, but at the GODO, as you mentioned earlier, Victoria, we have two plane waves, and one of them's got the imager, but the other one has a spectrograph, which really lets us explain these complementary ways of doing astronomical observing.
Mm-hmm. And it's really exciting to be able to have a spectrograph In my own research, I do a form of spectroscopy, so it's really neat to be able to share kind of the scientific tools with people as well, and being able to show them how this is the different values of, say, absorption or emission for all these different colors of light, all these different wavelengths, and then compare it to what we see. We do this quite a bit with things like the Ring Nebula, because we can compare the spectra of dying stars with the spectra of our sun and show how it shifts as well. It's fascinating to be able to show people at least closer to what data looks like. And from a science education perspective, it's a lot of fun too, because I have fun with doing research, and a lot of the reason why I'm here and why I do my job is because I want to share that with other people. So it's a really fun avenue.
It is a lot of fun. I miss the Meet an Astronomer nights with tons of people up there. Of course, we can't do that right now, but hopefully we will get back to the point where we can. And I would just mention for viewers who might be interested in the properties of our cameras, if you want the details, this sort of goes back to the question from Terry. I looked it up quickly because I'd forgotten the URL, but it's Malincam with 2 L's, malincam.net. And they have all the information about them, about their different cameras there. So I think you have one more really cool object for us, Victoria.
I do. It's a favorite in the night sky, the Orion Nebula. And this one is always a lot of fun to use with, or to talk about with guests, because it looks incredible through a telescope. You can see a lot of the detail. You can pick out stars. You can pick out gas clouds. You can see it with the unaided eye as well. It looks like a big star, or just a bright star in Orion's sword. And it turns out pretty phenomenally in pictures as well. Even with a maybe not the most advanced CCD, we can still get these different colors, the structure in the gas clouds here as well. This bright spot in the middle is actually a set of stars called Trapezium, and with a telescope, you can see them individually, which is really neat with a large enough telescope, which isn't too large. Even telescopes as small as 12 inches, you could pick out 4 of the Trapezium stars easily.
And these are baby stars, just being born from this cloud. We sometimes call these stellar nurseries, because this is where new stars and new light are kind of joining the galaxy, and Orion is one of the more nearby of these regions. Yep,
these are all young baby stars, and the really neat thing about this newer image is that you can see almost through the gas, and a lot of these tiny little fainter stars are in fact just behind this cloud of gas and dust. And especially with some of our newer telescopes, like our 32-inch Dobsonian up at the Godo, you can see some of these throughout the gas cloud. They look like little flecks of glitter, and it's incredible. The Orion Nebula is one of the best objects to be able to engage with people, because even if they're waiting in line for a telescope, they can still see it with their eye in the sky. And then they can get up to the telescope and see it in more detail. And then even with a telescope, you can't necessarily see a lot of the colors, simply because our eye doesn't take a long enough picture to take in enough light to see that. So instead, when they come over to our photographic telescopes, we can instead show them the incredible level of detail that we can achieve, and see more of the colors and the structure in more and more detail.
Right, although I think with the 32-inch star structure telescope at the Godo, that is enough aperture that you can pick up some color on some of the brighter nebulae, because even though your eye is not integrating, that large aperture is collecting enough light to trigger the cones in your eye and deliver some color.
Definitely, you can see faint hues. It's not, the vibrant pink that you might see here, but right. You can see it, the suggestion of pink.
And so, I don't know, have you had a chance to looked through the eyepiece at the Lowell Discovery Telescope, which is 4.3 meters of aperture?
I have not. I have not yet. Every time I sign up, it's clouded out.
I know, that's too bad. A number of staff have, and yeah, I think I've looked through the eyepiece there when we could have it mounted. We don't right now because the instrument cube is fully populated with instruments. But man, looking through that thing with an eyepiece, you've got so much glass that the most impressive things to look at are the nebulae, because the color is just exploding out, and it's really amazing to see. So as we ask for any final questions, so for this interactive stargazing, which we're trying to do, I think roughly weekly, basically people can log on to the YouTube channel and see images like this sort of on request. I mean, obviously we couldn't do Orion right now because it's not the right season, but in general, that's how you handle it, as I recall.
Yes, and that's very similar to how we handle it in person as well, which I think it's wonderful that we're able to bring closer to what our programs used to be,
right,
to the virtual setting.
Yeah, I recall that from the recent meeting. Astronomers, very often you'll get chatting with the guests and they'll say something that will trigger something in your mind. It's like, oh, if we want to talk about that, it would make sense to go to this object. And it could be a nebula or a planet or a double star or something. And it's just really neat to have that flexibility. And now you just tap an iPad and it just goes there. It's so cool. So I'll note that our next interactive stargazing will be Tuesday, June 30th, 9 p.m. Arizona time, which is Mountain Standard Time, and it's the same as Pacific Daylight Time. And so unfortunately that's midnight on the East Coast, because it doesn't really get dark here until about 9 at this time of year. So, okay, well, this is really cool. We really enjoy bringing all of this to the public, and just want to say thanks for joining us today. Thank you very much, Victoria, for taking us on a tour of what our facilities can bring, and we'll look forward to seeing everybody online, and hopefully just as soon as we can responsibly do so, in person once again. So from all of us here at Lowell Observatory, as always, stay healthy, stay well, and hope to see you all again soon. Bye.
Bye.